In this video, we're going to be learning about a family of hydrocarbons that contain triple carbon-to-carbon bonds, such as the simple molecule that we see here. This is the simplest form of a family that we call the alkynes, indicated by the suffix YNE, and we'll see that this suffix appears in the name of this simple molecule here. So we can actually derive the name. There we see that there are two carbons in the parent chain, which means that we identify it with the prefix eth, and the suffix YNE indicates the presence of a triple carbon-to-carbon bond, and so this molecule would be named ethyne. Now, the first distinction that we want to make between alkynes and alkenes is the discussion of whether alkynes, like alkenes, have the same EZ isomer distinction based on their geometry. Now, we remember the reason why alkenes have EZ isomerism is if we analyze the AXE configuration of each of the carbons in the double bond, we see that each of those carbons is AX3, meaning that in addition to the double bond, each carbon can also have two additional atoms bonded to it like this. So let's get rid of one of the hydrogens, and let's say that that hydrogen is a chlorine instead. And then let's do the same on this side here. So we can remember that because this double bond is not able to rotate the way that single bonded atoms are, because the double bond increases the amount of resistance that this bond has to rotating. Therefore, each of these chlorines is stuck in its respective position, and if the chlorine here was pointed up while the chlorine here was pointed down, this would be the E isomer because the two chlorines are on opposite sides. However, this distinction makes no sense when looking at an alkyne because the AXE configuration of each of the carbons in the alkyne is only AX2, which means that in addition to the other carbon of the triple bond, each AX2 carbon can only contain one other attachment, which is the hydrogen here, which cannot be pointed up or pointed down because the geometry of an AX2 atom is always going to have each of the attachments 180 degrees apart. So EZ isomerism makes no sense when it comes to an alkyne versus an alkene. Now, the good news about this is that it makes alkynes relatively straightforward to name because there isn't a second isomer that we need to worry about based on EZ positioning across a double bond, because across a triple bond, this is impossible. Therefore, the only trick is actually recognizing how many carbons an alkyne has, because the geometry of an alkyne always has the atoms across from the triple bond 180 degrees apart, which makes counting carbons a little bit tricky if you aren't prepared. So if we start here, recognizing that this can be carbon 1 not just because it puts the side chain length or side chain location indicators at the lowest number, but it also puts the triple bond in the lowest position as well, and that is critical. Now, we can recognize that carbon 2 and carbon 3 are here because even though all of these carbons are in a straight line, you need two carbons joined at each end of the triple bond like this, and then it becomes a fairly simple matter to count the rest of the longest carbon chain. So this would be 4, 5, 6, 7. So our parent chain in this case is going to be hept because there are 7 carbons, and then we see that our triple bond is in position 2, so the parent chain would be called hept 2. And if we identify the rest of our side chains here, we can see that on carbons 5 and 6 we have 2 methyl groups, so we would identify dimethyl here. Then on carbon 4, we have a single ethyl side chain here. And then on carbon 1, of course, we have our alphabetically first side chain, a bromo. And then immediately after that, we have 1,1-dichloro to indicate 2 chlorines on carbon as well. And we can see bromo comes first, followed by chloro, followed by ethyl, followed by methyl. So let's go ahead and write all of those side chains in the proper order. I almost forgot the numerical prefix dichloro to indicate that there are 2. There's only 1 ethyl, so no numerical prefix is necessary for ethyl. And then we have our alphabetically last side chain, the 5,6 dimethyl. And then I'm going to have to squeeze the parent chain name in here, hept, and then with the location number 2 to indicate the presence of the triple bond YNE. Now, if we want to do one practice example in terms of drawing, this one we've made easy because the triple bond is actually in location number 1. So the first thing I'd recommend doing is to draw the triple bond out like this. And again, don't hesitate to label that carbon 1 is here and carbon 2 is here. We see that our parent chain is also 7 carbons long. So if we remember that because we have AX2 geometry here, the angle between carbon 2 and carbon 3 also needs to be 180 degrees, but then the rest of the molecule can look relatively straightforward with the typical alkane zigzag that we see here. So 3, 4, 5, 6. Let's just double check. 1, 2, 3, 4, 5, 6, 7, and there is our parent chain. Then on carbon 3 and 4, we have an ethyl group, so let's draw 1 ethyl on 4 and 1 ethyl on 3 so that we are good. And then on carbons 5 and 6 that we have here, we have substituted iodines, which we can write in like this. And lo and behold, we see yet again that representing alkynes is always easier than actually naming an alkyne from a given structure. All you need to do, number 1, is I would recommend identify and draw the triple bond location first, and remember that because each of the carbons in the triple bond is an AX2 carbon, that we need an angle of 180 degrees between all atoms associated with them. But other than that, the naming and drawing system remains identical. In the next video, we're going to be examining a set of isomers of alkynes, only that don't have triple bonds, but that actually combine our knowledge of double bonds with our knowledge of drawing ring structures.